Okay, we should probably get started. So, thanks for joining me. My name's Andrew Whitechapel. I'm a PM on the DevPlat team in Windows Phone. And I'm going to talk today about the resource manager in Windows Phone and how your app can cooperate with the resource manager to make it more robust and also to improve the user's experience of your app. So I'll give you a heads up. This is very much an infrastructure talk. There's no shiny user-focused features here. No singing and dancing. So if you're looking for something exciting, the door's back there. I'm aware that some of you are probably kind of working through the hangover from last night. So I'm going to keep this low-key. In fact, my aim is to make this as boring as possible so that everybody falls asleep, and then we can all go home relaxed. So this is what I'm going to talk about. You would think that the platform takes care of resources and that your app can do whatever it likes. Surely, we provide you an environment in which your app can run, so why can't you just get on and do whatever you feel like? Well, you can, but there's a cost to that, and I'll talk about what that cost is and what your choices are. And then from there, I'll kind of switch gears and go into sort of a deep dive into the resource manager, and this is where it gets really boring because, it's interesting to me because it's one of the components that I own in the platform, but it's more to give you an idea of why we're doing things and why there are these constraints, and so that you can understand the logic behind it, and so you can sort of navigate your way through what the system is doing, so that you can cooperate within that system, as opposed to fighting it all the time. Memory is probably the most interesting of the resources that we manage as far as your app is concerned. And it's certainly the one where we provide the most API surface for you to twiddle the knobs and dials. And all the way through, I'll call out anything that's different in blue. It's not a separate thing on the end. So why do you care? And for some of you, this will be obvious, but it's worth calling out. There are kind of two dimensions to this. One is that I'm making the assertion that you want your app to be available on the widest possible range of devices, to the widest possible market of users. And actually, there's kind of a series of steps. You want it to be available, but you also want it to run on all those devices. And those aren't necessarily the same thing. And it's not even enough for it to run. You want it to run well. You want the user to have a good experience. You want them to give you good ratings. You want them to recommend it to their friends. And you want it to run well all the time. And that sort of scale of requirements actually is quite difficult to achieve. Because the flip side of this is that you are running in a very constrained device. Obviously, it's a small form factor. We have a very small amount of memory, typically. We have a slow processor. The flash drive is probably small and probably slow, relative to, say, a desktop PC or a tablet even. But at the same time, we're on this convergence trajectory with Windows. And so since version 8 of Windows Phone, we've actually had the Windows NT kernel on the phone. So you've basically got a desktop OS on a phone. So that does make it difficult for us in the platform to manage the very tight constraints. I mean, when we went from 7 to 8, the OS and the drivers and services basically jumped from about 65 meg to about 300 meg. And so that's eating into the memory space available for everything else, for your apps and for background tasks and so on. So convergence is a good thing, but there's a cost to that. Another dimension to this is the addressable market. A few years back, it seemed to be the pattern that you would target the highest spec device because smartphones at the time they started off as an elitist thing, that the latest and greatest thing that came out always had a higher spec, and that's what people targeted. And if your app didn't work on a down-level phone, you didn't care too much because everybody was buying the new thing. Well, that's not true anymore. It hasn't been true for a while. The growth in sales of devices is very much in the mid-tier range. So, it's why the emulator, the default emulator in Visual Studio is a 512 meg device. It's because that's what we want you to target, because that's where the growth area is. Vast majority, overwhelmingly more phones are sold at that range than in the sort of premium range. So you really want to make sure your app works down at that level, and then obviously it will work on the higher spec devices as well. So you have some choices, though. As I said, you could just ignore the platform entirely and just do whatever you feel like. We provide an environment, we cap your memory and cap your CPU quota and so on, and you could just ignore everything and just use the APIs we give you and do what you like. You have some choices. Selective targeting, which I'm saying means you're actually reducing the size of your market. You're saying, I specifically don't want to be available on certain devices. Either because they don't have enough memory or because they don't have the other sensor resources that I require. Or you can go the other way and say, well, I will try and be flexible, and I'll figure out what I'm actually running on at runtime and make choices at runtime according to whether there's enough memory for what I want to do or whether there's the particular sensor that I require. So if you want to do selective targeting, if you want to reduce the size of your market because your app is so complex and it actually requires certain features, like it must have a front-facing camera and a compass, and it must have at least a gig of memory, then you can do that. You could say, well, for some set of apps, they're simple enough that they will just run on all devices anyway because they don't need a front-facing camera and a compass and 1 gig of memory. They're perfectly happy without those features. And so that's easy enough. But you can also, in your app manifest, you can specify requirements that say, I must have, ID Rec magnetometer, I must have a compass, or ID Rec memory 300, I must have at least a gig of memory. And what happens there is that the app is filtered out in the store. So a user with a 512 meg phone looking at the store, they won't see your app if you've specified that you require at least a gig of memory. So it's just not visible to them. So that's an option. And again, it depends on your app. If you really just can't get it down within that small memory size, or you absolutely require this sensor that's not always available, that's a reasonable approach. But my assertion here is that you would try to avoid this situation as much as possible. And that even if you require some sensor for some part of your app, you can degrade gracefully if it's not available. You can say, okay, this feature behaves like, I use some kind of backup mechanism or an alternative which is not quite the same, but still allows your app to be available on all phones, even if it doesn't behave quite the same on all phones. So flexibility is a more interesting approach, I think. Is this thing available that I need? Is this resource, whatever the resource is it available? And there's a couple of ways that this works. I'm going to actually show you a demo, I think, at this point. Let me switch to my demo machine. This one. Let me just run this. So this is interrogating the system that it finds itself on to find out which of all of the things that might not be available are actually available, and what do they look like. Is there a camera? In which case, what kind of camera is there? Is there a compass? How much memory is there? What version of the platform is this? And so on. So some of these things obviously change. Some of them are fixed per device, like the hardware sensors, the camera. Is there a front-facing camera? That's always going to be true. It's not going to change over the lifetime of the device. Some things will be fixed for the run of the app, but not necessarily. Like the version of the platform could change on the device over time, even though when you run your app, you only need to ask for that once because it's not going to change while your app is running. And then there's obviously a set of things that will change dynamically as the user does things, as they move in and out of Wi-Fi, as the Wi-Fi signal deteriorates. If they go over data, if they go into a roaming area, if their battery becomes low, if they plug into AC power, all of those things will change dynamically. So you can obviously query for all of these things, and it's pretty straightforward. If you look at the code, there's enough API surface here for you to query for anything that's optional. So is there a gyroscope? Is there an accelerometer? The camera, is it an ordinary camera or is it the front-facing camera? What's my screen resolution? You can get that. There's a very simple mapping from the scale factor. You can figure out whether it's WVGA or WXGA or 1080p or whatever. The version, you know, there's a published list of version numbers. So if you know that this feature was only available in version 7.8 onwards, then you can query, you know, find out what the current version is and is it greater than or equal to the version you're interested in, and so on. And then things that change at runtime. Is cellular data enabled? Is roaming enabled? And so on. What kind of network have I got? Am I over my data limit for my paid service? And there are a number of events that you can sync where as these things change, an event is raised and you can look at it and then, you know, perform the appropriate action on that basis. So that's a better way to approach things than just to reduce the availability of your app, is to query the system, find out what I've got, and make alternative choices. I think I've talked about this. So now let's look at the resource manager. The question up front, it may not be obvious. We cap your memory, we restrict your CPU quota, we restrict access to sensors under certain circumstances. And in the converged model, we can also actually restrict your network bandwidth usage. So there's a lot of constraints, and it's like a policeman in the background saying, you must do this, or you must not do that, or no, you can't do the thing that's perfectly reasonable that you want to do. But the reason at a high level is that there's a number of different things running on the phone at the same time, and obviously there's resource contention. It's not just the case that the user's working with a foreground app and nothing else is running. Now, we could set it up like that. We could say that obviously if the user's running, you know, Temple Run, then they want to be playing Temple Run and they don't care what else is going on. So we could say, right, Temple Run gets everything, all the memory, all the CPU. We don't allow anything else to run in the background. We could do that. But users have expectations of the overall functionality of the phone. Even if they're playing Temple Run, they expect to be able to get an incoming call. So we can't give all the memory to Temple Run, otherwise we couldn't take the incoming call. And if it's an incoming VoIP call, then there's actually more memory involved in that. And the classic case is email sync. You know, they look at email, and then they start playing Temple Run for an hour or so, and then they go back to email. They would expect their email to have synced, at least partially, in the background while they've been playing Temple Run. They don't expect to go to email and then have to sit and wait there for 5 minutes while it syncs 200 email messages. You know, maybe half a dozen messages are being synced, but they would expect some syncing will have happened already. So this is the general pattern that we try to maintain, is that there are scenarios that we try to protect. It's not just the foreground. It's a foreground in combination with whatever else they might want to do next. So we have to allow things to continue to run in the background. And that's why we maintain these checks and balances so that no single process can run away with all of the resources. And the things we manage are, as I said, memory, CPU. We do it by a notion of priorities, which is based on scenarios, which I'll talk about in a second. And you can feel free to fall asleep. I mean, it's okay. This is deliberately boring. I've got a couple of tables to show you. I don't want to go through every single row and column, but just to give you a pattern, this is the memory caps for Windows Phone 8 GDR3, which you may or may not have on your device right now. A couple of things to call out. Clearly, the memory cap value increases as the memory on the device increases, in most cases. So a VoIP background agent gets 51 meg on a 512 device, but it gets 60 if it's on a 1 gig device, and it gets 80 on a 2 gig device. So it can do more things on a bigger device, but it should still be able to do its basic functionality on a 512 meg device. Some things like background audio and background agents on a 512 meg device, they are deferred from running. We prevent them from executing while there's a VoIP call going on, because we need that memory for the VoIP call. And this is one of those cases where we decide that the user scenario dictates that the VoIP call is more important, because this is something the user is interacting with directly. And that while the background audio and the GBA is important, it's not as important. So on a 512 meg device where we have very limited resources, we just defer those. We queue them up until the VoIP call has finished. Whereas on a 1 gig device, we've got enough spare memory to allow those to run at the same time. Although, again, in the case of VoIP and background audio, that generally doesn't make sense, because you're not going to be playing music at the same time as you're talking on the phone. And another thing to call out, which has changed in blue, is the last row there, the foreground app cap. We had this mechanism in 8 where we said there was a minimum cap and a maximum cap. And everybody got the minimum cap by default, but you could request the maximum cap in your manifest, and we would just give it to you. I mean, the idea was that we preferred people to stay at the minimum cap and not use up to the maximum cap. But that's changed in blue. And I'll show you how that's changed in blue. So this is a summary of the blue caps. It's not a complete list. It's a list where I've pulled out different task types where their memory cap is different. But there's a longer list, which is documented, which lists things like the lifetime cap on this, the CPU quota on this, and so on, because those things also change. But I'm focused here on memory. So you can see, even at a glance, that obviously there's more different task types. There's more stuff that could be running at the same time. Also, the caps in general are either the same as they were in 8 or they're higher. And we've done away with the min cap. So everybody gets the max cap now. You don't have to ask for it, you just get the max cap. And a couple of things to call out there are those two sets of caps, the Windows Phone 8 generic background agents as opposed to the Windows Phone 8.1 modern background tasks. So if you have a Silverlight GBA as opposed to a modern XAML background task, their caps are slightly different. And that's because they use memory differently. Same with the foreground app. If you've got a Silverlight foreground app as opposed to a modern XAML foreground app, they get different caps because they use memory differently. And we're fairly precise about exactly where the memory is going and how it's being used. And an added quirk to that is if you have a Silverlight 8.0 app that you've upgraded to Silverlight 8.1, that's now running on the modern stack, and therefore it gets the modern caps. So there's a couple of dimensions to this. I mentioned you can put some entries in your manifest. I'm saying you should probably avoid doing this. The first one, the ID rec memory entry in the manifest says I require, it's saying I want to run on a device that's got at least 1 gig of memory, and the entry at the bottom is the equivalent in the modern package AppX manifest to say I must have at least 1 gig of memory. And this is the thing that filters you out in the store if for a device that doesn't have at least 1 gig of memory. And then the one in the middle is for the higher cap, the max cap, which is just ignored because everybody gets the max cap now. Some simple math. I'm trying to drive home this is a defensive thing. We do restrict your memory, we restrict your CPU, and there is a reason for it. If you look at the math here, on a 512 meg device, which is the most interesting device, if we assume a paging level of about 80% of the page file, so we have a 256 meg page file, if we page at about 200 meg, that's where it's still acceptable. You're not thrashing on the disk. We're not using up the whole page file. That gives us around 712 meg of memory. And then there's a series of things that we pretty much have to carve out as reserves. So the board support package, this is the software that drives the motherboard. It's around 130 meg. the kernel itself, plus the drivers, plus the services, the SCUM services on the system, they take another 300 or so. It varies according to device, but these are reasonably accurate numbers. So those things have to carve out the memory. The equipment manufacturer, the device manufacturer, and the mobile operator can also deploy service agents. Now, there's a dividing line there between the things that we resource manage in the app platform and the things that we don't. So we don't resource manage the BSP and the drivers and the services, but we do resource manage the service agents, for example, that Nokia or Verizon or AT&T have put on the device. So we manage them in the sense that we cap them, but we still pretty much have to guarantee that they can run. Same with voice over IP, background audio. We have to guarantee that those can run anytime they want to run. Bluetooth, there are actually different types of Bluetooth. I don't know if anyone was in Vijay's session and Jim's session just before, but for long-running Bluetooth, this is the heart rate monitor scenario. Once it's running, we want that to be able to continue to run, and it doesn't make a lot of sense if it can't run. And VPN, if you've got VPN set up on your device, then that's going to have to run all the time. So there are things that are carved out that even though we manage them, we have to guarantee that they can run. So that leaves us 180, more or less, for the foreground app and all the opportunistic things, which includes apps in the back stack, continuous background execution for things like turn by turn, and all non-critical background agents and background tasks. And if you remember, the cap for the foreground app is 180. So if all of those things are running and they're all consuming all of their caps, then there's nothing left for the opportunistic stuff. But as it turns out, most of the time, we play a percentages game, most of the time, apps don't use their max cap. Smaller things like background agents and background tasks use much closer to their cap than big things like a foreground app. But typically, a foreground app does not use 180 meg, even though that's its cap. It can use up to 180 meg, but it doesn't usually do that, which means that, on average, it's using a lot less than 100 meg. And that means we've got 80 meg free for other things that we can run. And so we do. And the flip side of that is that because we only run those when we've got memory, they may or may not run when you expect them to run. The percentages turn out, after very extensive app compat testing for a long, long time, the percentages turn out that most of the time, the vast majority of the time, these things do run when they expect to run. There's no guarantee, but it just turns out in practice that they do. But it's always possible for somebody to write an app that is going to consume 180 meg instantly and forever, so long as it's running, and then those other things are going to be deferred. So this is part of what I was talking about earlier about trying to maintain a balance in the ecosystem. If you write your app so that it does consume its max cap, then you are preventing other things from running, including your own background agents potentially, as well as things that the user is expecting to happen in the background. And users, they might not know they haven't been to this talk, they won't know what's actually going on, but they'll soon figure it out that every time they run this app, it takes a long time to sync email afterwards, or every time they run this app, my tiles don't get updated. They'll figure it out after a while. I think this is the last, no, it's not the last, it's the penultimate table. I said we have a notion of priorities. So this determines when things get to run, when there's contention. So we assign priorities to the foreground app, VoIP, background audio, and so on. They all have P2. P1 is cellular calls. Cellular calls must always be able to run in and out. And then slightly below that foreground app, whenever the user goes to the start menu and taps the tile, we must be able to run that. Same with incoming VoIP and so on. But then as you go down the list, things have lower priority. And down at the very bottom, we have the GBAs and the background tasks. These are very opportunistic. They'll only run if there's memory free. And the corollary also is if we're running these things, these low priority things, and then we come under resource pressure, particularly memory pressure. So the foreground app is only using, say, 100, and so we run a load of things in the background. And then the foreground app spikes because the user's gone to another level, and suddenly the memory goes up, and it's loading a whole new load of textures or whatever it is doing. At that point, we have to honor that requirement from the foreground app because it's higher priority. So we'll start killing things in the background. Things that were opportunistic in the first place, that were never guaranteed. We'll start to terminate those in reverse order of priority. And actually, off the bottom of this list, I didn't put it on, but the bottom row on this list would be things in the backstack. Things that have already been paused, they've already cleaned up their state, they're just sitting in the backstack where they may or may not be resumed ever. They'll be the first to go, because they're probably sitting on a lot of memory as well. So we'll kill those, then we'll kill the GBAs and the background tasks, all the non-critical things. Then we'll kill CBE. If you think about it, the things at the bottom tend to be pretty small, so the chances of CBE getting killed are actually fairly high, because that's sitting on 150 meg typically. But we'll walk up in reverse order and kill stuff. Some things you can do in the API. Since 7, you've had a couple of properties on the device status class that you can look at to find out the two interesting metrics, which are what is your cap on this device and how much memory you're currently using. And therefore, obviously, you can subtract one from the other to figure out what your headroom is. And then in 8, we introduced a memory manager class specific to the phone that provided exactly the same information. So you could use either one. And in Blue, we've provided another memory manager class. It seems like we can't make up our minds what we're doing here, which is partly true. But this memory manager class is converged with Windows. It's not phone specific. It's a Windows standard iMemory manager interface. And again, you get the same information. You can get the cap, you can get the current usage. We also give you some events that tell you when your app is increasing or decreasing in its consumption. And not just randomly increasing or decreasing, but at certain key points. We've defined 3 levels, high, medium, and low. And whenever you cross a threshold from low to medium, or medium to high, or high to medium and medium to low, we'll raise the event so that you know you're moving from one band to another. Let me show you a demo of this. I think actually I will run this in the debugger. So this is a simple app. It's just querying its current memory. And you can see it's figured out that, okay, the device is 512. My cap is 185, because this is a Silverlight 8.1 app, so it's using the modern context cap. Currently using 9.91 meg, usage level is low. Now I have these 2 buttons, and what they're doing in the code there, you can see, is just grabbing chunks of memory in 10 meg blocks. That's all they do. It's kind of simulating doing something interesting that you know is consuming memory. And I'm deliberately logging this at the beginning and end. I'm saying, well, okay, at the start of this, this is almost, it's like an additional diagnostic that you could do. So at the beginning of some chunk of code that you know is memory consumptive, figure out what you've got at the start, do your thing, figure out what you've got at the end. And that will tell you whether you need to tune this for memory consumption. So as I click this, you see it's reporting down with debug write lines down here. It's just looking at what's my current usage and what's my headroom based on the cap. So I can keep grabbing 10 meg chunks. And eventually, I'll get to the point where I cross this threshold from low to medium. And you can see I've received an on-app memory usage increased event. And all I'm doing in there is, where is it? All I'm doing there is changing the color of the brush, that's all, really. But, typically you would actually do something useful in there. And I can keep going up, and eventually, again, I'll go from medium to high. Oops, and now I've crashed. This is very interesting. Let me run this again. Hold on. Partly it's because this is an artificial scenario where I'm grabbing 10 meg chunks every time, which is more than you would normally do. But there's 2 things to say about this. One is that when I get to high, so you can see it's reported down here, I've got 166, 168 meg, and I've got 18 meg of headroom, so I ought to be able to get another 10 meg chunk you would think. Well, let's see. Okay, so I can. 176, given my cap is 185, you'd expect I can't get another 10 meg chunk. So what happens? If I continue to do this thing, and if I'm ignoring these events, and I continue to do this thing that I know is consuming lots of memory, I get an out-of-memory exception, because I am actually try-catching up here. So I am catching the out-of-memory exceptions. It's not necessarily the end of the world. We won't, the caps are enforced by kernel job objects. You cannot exceed the cap. Any allocation that would take you above the cap will fail. And in a managed app, it's surfaced as an out-of-memory exception, which you can handle if you're smart. If you don't handle it, if you just ignore it, then it will propagate out and we'll treat it as a crash. We'll basically terminate the process. So you can handle it and take mitigating action. But let's see if I can repro that crash. No. See, I can keep trying to grab memory, and it keeps on throwing exceptions, but it's not giving me any more. But there is scope, as you saw earlier. I mean, that's not a bug in the app. There is scope for you to crash because depending on what's actually happening and what it is that you're doing that's causing this memory allocation, you may or may not actually get an out-of-memory exception. Most of the time you will, but you might not. So there is a very small window. So I guess the thing to take away from that is that we give you these bands, low, medium, high. You really want to be in low and medium all the time. You don't really want to be in high ever. So if you sync the events and you go into high, you want to do something immediately to come back down. You don't want to carry on doing whatever it was you were doing that's consuming more memory. Because even if you're catching the exception, you may or may not actually get it. Plus, I'm allocating in 10 meg chunks, so there's going to be I'm not going to get close to my 185 meg cap. If I was allocating in 1K chunks, then I would get very close to my cap before it failed. But other things happen as part of the allocation. You might think that this object that you've created is exactly this number of bytes, but in order to allocate memory for that, other stuff is happening, which is also allocating memory that's attributed to your process. So there's more memory being allocated than you think. So just watch those events. Don't be in high ever. Okay. Here's another interesting event. Let me switch to this. So I have a CBE app here. So let's turn on location. So it's tracking location, and I can simulate going into the background in the emulator. You just press F12, and it goes into the background. And you can see here that I've actually received an app memory usage limit changing event. Old limit was 185, new limit is 150. Because even in Phone 8, we said that when a CBE app, when you go to the background, your cap is going to be reduced to 150. So now we're actually raising an event, so you can see when this happens. And the thing is still running in the background, obviously. It's still tracking. So I can tap on the toast and go back into the foreground, at which point I should get another event saying that, okay, your cap has now changed again. So there's only a couple of scenarios where we change the cap at runtime. The rest of the time, the caps are published, and they're static and they don't change. But for the CBE scenario and for VoIP scenarios, where these are things that start in the foreground and then continue in the background, we will change the cap at that transition point in both directions. So you need to pay attention to those events. Okay, this is the last table. I mentioned we constrain memory, CPU, and sensor resources. And the sensor resources are kind of easy. It's a Boolean almost. You can think of it as, if you're in the foreground, you've probably got access to most things, if not everything. But if you're in the background, you know there's going to be a restricted set of things that you can't access. And it's mostly for privacy reasons. So if you're a background audio agent, you can't use the microphone, you can't use the camera, for example, in the background, which kind of makes sense. You can use proximity and the gyroscope and the compass, fine. You can use speech synthesis, but not speech recognition. So I would think these are kind of obvious when you look at them, but the point is for every different task type, if it's in the background, it'll have a subset of sensors available to it. So again, it goes back to you should query the system. First of all, is this sensor actually physically available on the device? Okay. Is it the type that I'm interested in? Is it a front-facing camera or a rear-facing camera? And then secondly, at runtime, because it changes, have I actually got permission to use this thing right now? There was a talk yesterday. Sean Henry did a great talk on background tasks with all the ins and outs of how they work, because again, this is another area that's been converged very much with Windows. But a couple of interesting things to call out from a resource perspective. We had a model in Windows Phone 8 for constraining CPU for background tasks, and we converged on the Windows model for Blue. So it's a completely different model underneath, but we've configured the values such that we think we're in almost exactly the same place as we were in 8, although the mechanisms are totally different underneath, and there's kind of Windows standard background manager BI mechanisms. We think we've arrived in the same place. But it is important to call request access async. I know that Sean called this out yesterday as well. This will ensure that your background task runs. So you would think that you wouldn't need to do this, and you don't need to do this. So it depends on how much work your background task is doing. If you can get away, if you profile your task and it does all its work and it completes okay every time you expect it to run, then fine. But this will actually bump your CPU priority or your CPU quota. So you might want to be calling that, and probably most of the time you will want to be calling that. This is for modern background tasks. Don't need to do that for GBAs. Bluetooth, I mentioned, this interesting there. There's two different types. There's the long-running type, which is the heart rate monitor thing. They run with a low priority, but we don't cap their lifetime. They can run forever. So you imagine you sync up with your heart rate monitor, and then you go for a run in the gym or around the park or whatever. You expect that to continue tracking your heart rate for the duration, however long that might take. You don't expect it to stop and start and be killed in the middle. So it has no lifetime cap, but it's relatively low priority. So if you start playing Temple Run and start getting incoming VoIP calls and start doing all sorts of other things on your phone, then there's a high chance that that thing will be terminated. As opposed to the short-running things, that's the key fob scenario. And these tend to be real-time critical, so we pretty much guarantee they have to run instantly. So they're very high priority, but the corollary is that, well, okay, if you're going to run at high priority, we're going to cap your lifetime. You can't do lots of work forever. Can't have it both ways. A note about graphics buffers. This was true in 8 as well. It's also true in Blue. If you're creating a background agent or a background task and you're expecting it to do things like creating wide tiles and creating lock screen wallpapers and so on, be aware that you will rapidly hit the memory cap if you create very high resolution multiple wallpapers, for example. So we've organized the caps such that they're still reasonably balanced with everything else on the system, and you can do most of the things you would want to do. You would create a medium tile, create a wide tile, or a couple of medium tiles, create a lock screen wallpaper. You can do those things. But if you want to create like 10 high-resolution lock screen wallpapers all at the same time and keep them in memory without flushing one each time you're going, then you're going to run out of memory. So be aware that you're going to hit your caps for the smaller tasks. You're going to hit your caps sooner than you are for the foreground app. And rude termination. This was also true in 8, but just to call it out, that you have to be prepared to be rudely terminated. If you're one of those opportunistic, non-critical background tasks, you'll get a certain amount of time to run. We believe that we've given you enough quota so that you can do anything that you would expect to do on a par with 8, the 25-second wall clock that you had in 8. But at any time we could terminate you because we may have launched you opportunistically in the first place. This is the scenario where the foreground app is not using its max caps. We run a whole load of things in the background, and then the foreground app spikes, so we start killing things. So be ready. Checkpoint your status as you go. Don't expect to get to the end of what you're doing and then save state. And this is another thing that's new in blue, so I should demo this as well. This is where you've got, what am I doing here? This is where we're sharing memory between the foreground and the background, which we didn't do in previous versions. So in this app, I've got two different, I'm doing a download, a background transfer, and I'm doing it in two different ways. So the top row of buttons is using the old Windows Phone 8 approach, using the background transfer service, and the bottom row is using the modern converged background downloader system. But if you see what happens to memory, so I've just got a timer that's updating memory as I go. So I'm at about 12 or 13 meg now. If I start an old style background transfer, okay, it goes up a little. I don't know how fast the connection is here, but maybe if I just, so either it completes or I cancel it, and memory kind of stabilizes out at around the same number. So it doesn't go up a lot, maybe goes up a little bit, maybe not. If I start a modern one, it jumps. It was around 12, 13, it jumped to 19, 20. And if I cancel that, or if it completes, then memory drops down again. And if I were to start, let's say, 3 of these things, or 4 of these things, the memory is going up. It's going up in 5 meg increments, because the background transfer task itself is taking up 5 meg. That's its cap. So in the past, in Windows Phone 8, when you did a background transfer, what happened is it kicked off a background transfer task, and that ran on your behalf, but we didn't take account of the memory that thing was using. And now we do, which you would think is horrible. But the fact is, you were kind of cheating. You were not deliberately, obviously. You were kind of getting away with using more memory for your scenario than we were allowing for when we were balancing everything out. So there was sort of memory that was kind of hidden that we were not counting for, and that upset our computation for everything else. So for the modern system now, for the modern background transfer, we do actually account for that background transfer task as part of your scenario. So something else to be aware of. A note about best practices. Stefan Wick had a talk on all of the various things that you can do to improve performance and improve your memory consumption, apart from the things that I've already talked about. And there's another talk as well about analyzing performance, which is mostly Windows Store app focused, but there are some elements that also apply. Well, the principles certainly apply to phone apps. Some of the tools involved don't, but some of them do. So it's worth going to those. There is, I think I've got time, there is just one more demo I wanted to show you. I wasn't sure if I'd actually get time for this, but let me quickly run through this. This is a note about image scaling. So in this app, I have a choice of different sizes. The image that I'm using, the original size is actually pretty big. So this is the size of the image file on disk, the resolution of the image file. But the control size that I'm using is that size. It's 444 by 300. But you can see the memory consumption down there. If I don't have anything, it's around 15. As I use bigger and bigger image sizes, so if I use the original size, for example, memory goes from 15 up to 60 meg. So I'm using an additional 45 meg just for that image. Because I'm doing the I don't care, you give me resources, I'll do whatever I like thing here. So I've got a huge image, and I'm not paying any attention to memory, and I'm just saying, use this image, put it in that control. But I have an option. If I set decode on, and then go to my image, you can see it's gone from 15 to looks like 15. Actually, I was expecting it to go a bit higher than that, but let's see. Not much more. It should actually be the same as this, the control size. And in the code, all it is, the only difference is I'm setting decode pixel width so that the image is decoded, if the JPEG image is decoded to the target size as opposed to decoded to its full original size and then scaled down. So obviously that uses less memory. But these are optional properties that you can set if you want to. Clearly you should. And this is a Silverlight app, the Silverlight 8.1 app as it happens, but if I just show you the equivalent modern XAML app, this is the Silverlight one still, waiting for the other one. Here we go, modern XAML one. Firstly, it's using less memory. I mean, these are identical kind of hello world apps. The XAML app is using less memory anyway, which is interesting. And if I don't set the decode on, so I don't use decode pixel width, and I ask for the original size, it goes up, but it only goes up to, it goes up about 10 meg. And in fact, if I pick the control size, you can see how the memory scales according to the image. So it definitely goes up, but it doesn't go up anywhere near as much as the Silverlight version. And if I turn decode on, so it's around 20 meg on the original image. I turn decode on and go back and load that, it's still around 20 meg. Point is, it doesn't make any difference in a modern XAML app because it's doing the decode for you, because we figured out that was the right thing to do. So Silverlight doesn't do it by default. Modern XAML does do it by default. So if you're in a Silverlight app, use that set decode pixel width and pixel height. If you're but consider whether you should be using a modern XAML app instead, because it's going to be using a lot less memory anyway, plus it's doing all the fancy decoding for you. I mean, it uses memory differently. It uses the GPU more than the CPU. But, okay, and I think that was all I was going to talk about. I think my battery might have died. Okay, so my recommendation is to try to support the widest range of devices, particularly 512 meg devices. So devices with restricted memory, slower processors, and not very fast flash. Those are the volume sales. That's what you really want to be targeting. And don't ignore the APIs that are given to you. Sync the events when things change, particularly memory. Pay attention to what's happening. Take part in the ecosystem so that the user has a good experience of your app, but also they don't see your app as some kind of rogue that affects the whole system. And there are tools and APIs that we provide that you can use for those. And I think that's it. Is anyone still awake? Yes. Okay, I will take questions. I don't know how questions work. I guess you talk to the mic? Is that how it works?
So with Blue, you have started.
Ooh. Okay.
Blue, you have started supporting SD cards, right?
Sorry, do we have what?
With Blue, Windows Phone Blue, I heard that you have started supporting SD card apps.
Yes.
So
Yes.
how, does it intersect with any of this? Like if I have a 512 MB device and I have a big SD card, does that give me any?
Well, the SD card only affects it doesn't affect runtime memory, obviously. It just affects where we're getting it from. We haven't noticed any significant perf differences in loading the app from SD card as opposed to loading it from the main flash. So there's nothing extra you need to do. It's kind of transparent to you where the app is. And the user can move it as well. It might start in one place and go to another. There's a selection in the settings for them to move it. So we didn't see any difference, so we don't provide any API for you to figure out where it is, because it shouldn't matter to you.
Also, there's no roadmap to actually use SD card to use it more as a...
Well, yes. So from a user's perspective, they're increasingly expecting to be able to use an SD card. And partly it's because they may have limited amount of flash on board anyway, so they will start by default installing apps onto the SD card. But from a developer's perspective, it shouldn't matter to you. Be aware that it may be on the SD card, but the point is that once it's running, it doesn't matter where it came from. It's not, from a system perspective, when we're listing all of the apps, for instance, in the app list, we need to know if they've taken the SD card out, then we need to pay attention to that. But that's not something you need to worry about.
The second question is, does the user come to know when you terminate these apps? Because as a Windows Phone user, the behavior for me is, with certain apps, there are more background tasks that resume fast, and with certain apps in the foreground, I see a lesser number of apps running in the background. There's no user feedback on which task got killed.
So the user's perception of what's running, so that they often won't know. They may not know that stuff is running in the background at all, and they won't know specifics about what's running, but they can go to the app list in the battery saver app, and that tells them, first of all, how much battery the thing is using and how often the thing was run and so on. And they can disable those or enable those. So if they realize that something that they're expecting to happen isn't happening, then they can go into that list and see if it's been disabled, and they can enable it. And there are a couple of settings there. I don't know if you already know this, but they can say, turn this on except when battery saver mode is on, or turn it on even if battery saver mode is on. So we force this thing to be running all the time. And we have a notion of how many things in the background can be run. And this is partly, the computation is based on how much battery consumption there is, based on how many things we run in the background, and how many of those we can run concurrently, and that's partly tied into how much memory we've got. But the default restriction in Windows Phone 8 was that you could only have 15 background tasks enabled on the device. And in 8.1, it's higher. It's either 20 or 30, depending on how much memory you've got on the system. But the user can actually override that. They can say, well, even though there's only 20 supposedly enabled, I'm going to enable everything. And then more things will be queued to run in the background. That doesn't necessarily mean that more things will actually run, because they're now fighting amongst each other. But they can, they can go to that list, and if they are aware of what's going on, if they notice that something they care about is not happening, they can tune that list to the things that they do care about.
Thank you.
You didn't talk much about how the garbage collector interacts with the memory limits. Can you talk a little bit about that? Does it force the garbage collection before it enforces memory caps?
Yes, the garbage collector kicks in, it kicks in at sort of random times as far as your app is concerned anyway, but it also specifically kicks in when we get to the high threshold, because the underlying warning that's sent to the system is sent to the Silverlight framework, for example, and to the XAML framework to say, okay, this app is going into high now. At this point, you need to do something to clean up, just in case they don't. So the framework does actually do a GC at that point anyway, as well as, according to its own algorithm of when it should be doing it.
Okay. Thank you.
Hi, I work on a turn-by-turn navigation app. Really appreciate the new event you added to notify us when the memory usage limit is changing. How much time do you think we have to start doing memory cleanups in between going from foreground to background and receiving that event?
So there's a catch. For VoIP, you'll probably get, it's CPU time, but you'll get enough time before we do anything to actually clean up. For CBE, you actually won't. You're basically for CBE apps, you're going to get that event. So it's almost like, so for VoIP, we'll send the event to say your cap is changing. Before we change it, we'll give you some time to do some stuff, and then we'll change it. For CBE, we don't. We send you that event, and we're saying it's changed. So it's kind of too late for you to do anything about it. We would like to have done the same as we do for VoIP. It was just a resourcing scheduling issue. So you could argue that that's a bug in the platform that we may fix in the GDR if we can. But yes, so in a VoIP app, you're fine. You've got time to do stuff. In a CB app, unfortunately, you don't.
Okay, thank you.
Should we be targeting Mango and Tango operating systems still, or would the 8.1 will be rolled out to these old devices?
So Tango is a very small set of the market. Mango is 7 and 8. I mean, if you want the broadest range, then target 7. Target 7 and light up for 8 and 8.1. It depends on your app as to how many of the new blue features you actually need. You know, if you want the broadest range, target the lowest common
So
denominator.
what would be the future for these devices? Now that the 8.1 can run on low-end devices, so the whole point was like the Mango devices were not able to upgrade to Phone 8 because it used to consume more memory. Right now that Phone 8.1 can run on low-end devices, would those guys get 8.1 on their devices, or
No.
it's
No,
end
so
of life for them?
eight devices upgrade to 8.1, but 7 devices don't. So
Okay.
there will, but also the number of 7 devices still in use is obviously going down over time.
Or the
Whereas the
Mango
number of
device.
8 and 8.1 devices will continue to go up. So the volume right now is in 8 devices on 512. So by all means target the whole range, including 7, but expect that number to drop off. And the 8-512 combination is the volume area.
Okay, thank you.
How is the memory fragmentation handled? I suppose we are allocating chunks of data and deleting only few. And is the memory allocated at the end of the stack, or is it properly handled within the OS?
Well, it's handled in the OS. I mean, the kernel takes care of fragmentation on its own. And we actually looked at that, and in fact, in 8.1, there are a couple of improvements in the kernel's memory management, mostly to do with paging. So paging is a lot faster, which is one of the reasons that we were cautious about raising what we considered the acceptable level of paging in Tango and in 8, because paging was relatively poor. It was quite slow, you know, combined with slow flash. But there are improvements in the kernel in 8.1, so it's actually a lot faster now. So we're happy to bump the paging level up, which actually, if you remember the math from that table, means that we can run more things that are taking up more memory than we ever did in 8, because we're taking more advantage of paging than we did before. So that's been improved. But memory fragmentation in general is a kernel issue. We looked at it. It looked fine. It was doing its job. There's nothing specific to the phone context that we felt that we had to make any changes for.
Okay. One more question. Suppose the user has switched off Bluetooth and doesn't have VPN or anything like that. So can the apps make use of that unused memory?
Well, yes and no, but remember the way the math works was that the 180 meg cap assumed
Is a
that
hard
all
limit.
of the other things actually didn't use their max cap anyway. But if none of those other things are running, so if you have a phone, it's a 512 meg device, your foreground app's got 180 meg cap, you don't have a VoIP app installed, so that's not being carved out, you don't have VPN, you don't have any Bluetooth, and you choose never to run background audio, then there will actually be some spare memory sitting there. But then we're going to use that to run other background things. So we're not going to give any more to the foreground.
Okay, so that's hard limit.
Yeah,
So-
180 will be a hard limit, or 185, depending on what the
Okay.
map type is.
Is there any chance that we could get that unused memory for apps in future?
No, because we want to maintain a balance. We know that there are other things that need to run, like
Okay.
email sync. You know, so we don't allow you to configure things so that you take everything. We want to keep I mean, you might think your app is the most important thing to the user, and it might be. I mean, you know, they might prefer for your app to have all the resources as well, but we have to maintain a balance across, you know, the range of users and what their expectations are. And so we give most resources to the thing that they're currently working with, but we keep a little behind for the other stuff in the background.
Thank you.
I have one question that's kind of slightly outside of that presentation. I was playing yesterday with memory management on the new Universal app, and I was able to reach all the features you showed today. That was working great. I noticed that the memory management moved from like a system.windows phone specific namespace to a Windows one. So I was expecting to be able to reach it inside a Universal app in a WinStore environment, and I couldn't. I was wondering
Right.
if you
No.
knew about it at all.
Yeah, no, I fudged that. I apologize. I fudged that a bit. It's true that it's converged, so it's not phone specific. The underlying interface, which is iMemory Manager Statics, I think is it's a Windows interface, so it is common. It's just that they don't have an implementation for it just yet. And the reason is that, you know, over time they've actually changed their position, but initially, like 2 years ago, Big Windows, when we talked to them about resource management, And they said, why do you manage memory? You know, we have loads of memory. Why do you care? We just let everything run forever. You know, the user's plugged into AC power all the time, so you don't need to manage it. So that position has changed, and it's continuing to change. So, you know, one step in that direction is that we do now have a shared interface and a shared component. It's just that their implementation, they haven't quite figured out what their values would be. I mean, we layer on policy that says that we think, you know, the foreground app should get this amount of memory and the various tasks should get this amount of memory. But that's phone-specific policy laid on top of a common memory manager component. And on the Windows side, they still have to figure out what their policy will look like, because they'll have different policy, obviously. You're going to have different caps all over the place. So that's not yet implemented.
Do you have any contact I can contact about those problems on Windows Store? Or do you have any names?
You're asking when that will be implemented?
Or when, or you know, what style?
Well, you can ping me, because I'm still working on the core resource manager across both Windows and phone.
Okay.
So not implemented yet, will be eventually. So you can get my email and
I will.
ping me.
What's the best way to diagnose hitting sort of these caps in background tasks? I've had instances where if I have a VoIP background agent, looking at like app usage, I assume I was around 30 megs, which is under 50. But then there are instances where after my VoIP task runs once, notify complete, no exceptions, it doesn't run subsequently, unless we reschedule the VoIP.
That shouldn't be true of VoIP. There are, for GBAs, if we see the thing crash repeatedly, we'll actually disable it.
That one I've seen, yeah.
But for VoIP, that shouldn't happen. We always allow VoIP to happen, even if it crashes repeatedly.
I've seen the behavior where that's not the case on certain
okay.
phones. So
yeah, I don't know. I mean, if you can get together a simple repro so we can take a look at
maybe,
it,
yeah.
that would be good, because that's not expected.
do you have like a card or anything?
Yeah. Well, actually, no.
I'll look at the slides.
Yeah.
And I assume emails on them?
I'm not sure that it is. Let me check. Well, I'll
Okay.
catch up with you. I'm being waved at. I think that's all the questions anyway. Okay, thank you.